Right. Let me also try this one. Okay, let's get started. First, are there any questions about the second assignment? Logistics of it? You're all aware it's released? Okay, good. Yeah, I recommend you start working on it soon. We have covered everything last time you would need to know for the assignment. So if you have never worked with any deep learning models, we do require, like you would like to use PyTorch. So if you have never used PyTorch, I do share a little Colab notebook you can use to kind of get a little bit familiar. So there is a lot of new stuff here. So depending on where you are with your machine learning, deep learning, I recommend stuff. I'm sorry, you had a raise?
Yes. Can I ask a question about the assignment?
If it's a specific question about assignment, let's keep it for the office hours. Like it's content, not logistics.
Yes.
Okay, yeah, please do. Just in case not everyone needs an answer to that question. Okay, let's get started. We lost, unfortunately, 10 minutes, and this is not a day where I planned that we will lose 10 minutes. So, all right, let's get going. Remember last time we learned about feed-forward neural network, and I told you that instead of these bag-of-words representations, we are going to now embrace this new notion where we have for every word its own embedding. And then with this kind of neural network, we said we are going to average this embedding to produce the representation of the entire text that these words make. And last time I told you, okay, don't worry right now what these vectors are exactly. I told you, just imagine we are having randomly initialized vectors of size 50, maybe 300, and we assume these are now weights of the model as well, and we are changing them as we learn the model. And today we are basically going to talk about how to produce these word vectors that are not randomly initialized, but are actually smarter. These vectors are such that we take vectors of two similar words. Their vectors are going to be close to each other, and if they are completely unrelated or have completely different meanings, the vectors will be very far from each other in a vector space where all these vectors live. So today the goal is to learn that. And just a quick, I don't have too much time for these demos now, but I did want to visualize what I mean by this kind of notion of similarity in vector space. So here we have some 3D space where we have projected vectors which are actually of the size 300. So each one of these like rows of colorful lines represent a vector of a single word, namely word man, woman, boy, girl, king, and queen. And the blue color indicates that we are closer to negative 0.2, and red color indicates we are close to the 0.2, positive 0.2. And if we have something that's almost like white, that would be 0. So you can see that here now, previously we had lots of zeros. Now in these 300-dimensional vectors, we don't have any zeros. We have blue and red lines of different intensities. So that's one thing to immediately notice. The other thing to notice is that instead of working with the sizes of the size of vocabulary, which are 30,000, 100,000, now we have only 50, 300, way smaller. And when you project these 300-dimensional vectors to a lower dimensional space, like 3D space, you can see that words that are somewhat related in meaning, but not completely synonyms, like father and uncle, are somewhat close in this vector space. And maybe father is very far away from princess, which is not the case for my dad. But you know, like it kind of shows you that these two words typically are not related to each other, and then they are far away in this vector space. And again, now today's lecture is all about how to learn these embeddings, these word vectors for words that we are going to then plug into another model. So I want to make it super clear. I noticed this was something that students have kind of got confused last time. So we have our deep averaging neural network, and this is our model with which we are doing classification. So this is a classification model. And its first layer is embedding layer. Remember when I said the first layer, now we are is going to be that embedding matrix, okay? So layer 1 here is embedding matrix or embedding layer that we use to look up vectors we need in given input. Now today, we are going to talk about another neural model to produce these nice word vectors. So this is where confusion comes from. I'm going to talk about today another model to produce these vectors. And then when I produce these nice word vectors, I'm going to completely forget about that model. And I'm just going to use embeddings I learned to be my embedding layer here. So we are talking about two separate models. So we have deep averaging network cover classification model. And then today we are going to talk about skip graph model. So it's going to be another model that whole purpose is to produce embeddings once. And once we produce those embeddings, they're going to become the first layer here. But otherwise, these are two separate models. So don't get confused about that. Okay, so now with all of that, I want to first motivate a little bit more various aspects of language that we care about that makes current representation we know, namely bag of words, DFIDF, all those word representations where we just occurrences of words, inappropriate for all the kinds of NLP tasks we want to model. So in general, knowing how similar two words are is going to be helpful for many NLP tasks. For example, paraphrasing. We want to know whether one question is a paraphrase of another, and this has various downstream applications. For example, when take a search engine, you might ask a query in many different ways, and if you want to have low latency, it's better that we understand that these are all similar questions and that we have already found the ranking of web pages for that query, and we just retrieve that ranking instead of calculating the ranking from scratch. If we want to detect plagiarism, for example, when you submit a paper to a conference, that should be unpublished work, and no other paper with exact same contributions should exist. So unfortunately, there are these practices where some organizations trying to just send papers into a conference, thinking maybe the program chairs won't notice that this is already an existing paper. And here it would be great if you can have a great paraphrase detection at the level of whole scientific article tool, which tells the program chairs, hey, you should be really careful about this one. I noticed there is a similarity with this other one. Summarization, producing a summary, giving a collection of text. This means that you also have some notion of understanding, this part of summary is going to paraphrase this part of the original article, and question answering, as I said, with search engine. So in general, understanding how similar words are to each other in meaning is going to be helpful for so many NLP applications. So let's go over a few. This is going to be more linguistics part of this lecture, like what are these aspects of meaning we care about. Here I'm showing you a screenshot from Dictionary for the word basin. First thing I want you to know that here in orange rectangle, you are seeing a lemma of this word, meaning its most canonical form from which you can produce a set of word forms. And word forms are just taking that lemma and changing it in some way. So for example, when we produce a plural of basins, we say basins, and we just added suffix s, and this is now a word form of basin. Here we have 5 different senses. We say word sense, and by word sense we mean a meaning of this word, and there can be 5 different senses. So when a word has multiple senses or multiple meanings, we say it's a polysemous word. And we have, underlying all of our NLP technology, we are basically doing word sense disambiguation. We're trying to understand which sense of the word are we using currently. And once you infer that sense, you can do stuff like understanding paraphrase, right? And another thing I want you to know is that we are talking now about meanings of words, and there is a whole field of study called lexical semantics that is studying the word meaning. So basically what we are talking about today is lexical semantics. And semantics in general deals with meaning, but not necessarily just words. It can be longer pieces of text. So lexical really refers to the fact that we are talking about meaning of words. Okay, so now we have synonyms. We say that 2 senses of 2 words are synonyms when one word has a sense whose meaning is nearly identical to a sense of another word. So such as canyon and gorgeous, these 2 words have, each one of them has a sense where then these 2 senses are matching. And practically, synonyms are those words that have more or less the same meaning in many, many, many contexts. But it's really hard to determine whether 2 words are exactly synonyms. So this is a little, linguistics trivia, but there is something called principle of contrast that says probably no 2 words are absolutely identical in meaning, and some difference in linguistic form. Linguistic form is basically what you see. So when we write the word and we see it, like we physically see it, that's a word's surface form. But its actual underlying meaning is not something we observe in a written way. Rather, we have this mental model of what its sense is. So when you have some difference in how we write 2 senses, there is a claim that there is always going to be some difference in meaning. And a great example of that is if I write to you H2O and water, these are 2 different written forms, different surface forms, but both of these forms are referring to water. And now, is this a synonym is the question, and linguists would disagree whether these are exactly synonyms. And this is just to illustrate that saying whether something is a synonym is not super trivial. Now I want to ask you how Bag of Word treats synonyms, and okay, here I wrote antonyms, but we'll come to them in a second. So if I have a sentence, she is brave and she is courageous, and I develop a vocabulary out of these 2 sentences, how would these two sentences, how would their representations look like? Yeah.
The words brave and courageous would be treated as completely independent of one another.
Exactly, right. And now, if you are thinking, we would basically have for first one, 1, 1, 1, 0, and for the other one, 1, 1, 0, 1. So the last 2 dimensions would be basically orthogonal in the vector space. And this would be completely different vector representations where these 2 sentences are basically saying the same thing. So we didn't capture any notion of similarity here. So if we were to do paraphrasing, question answering, search engines, summarization, everything we have mentioned with these representations, we would be quite limited. Similarly, antonyms are those senses that are opposite with respect to only one feature of meanings. So antonyms can define a binary opposition or be at opposite ends of a scale, something like hot and cold. and be reversive, such as ascend and descend. And again, for here we have two sentences. It is hot and it is cold. And again, we have represented them with different vectors, which is good. These are different sentences with different meanings. But we, in no way, we have hinted you are exactly opposite, right? How can you say another thing like it is warm, and it is warm will have a vector that is equally different from it's hot, then it's hot is different from it's cold, where we know that it's hot and it's cold, warm should be closer in the vector space. Okay, so although bag of words representations treat antonym as, distinct, they have distinct features, it doesn't record any special relationship between them where there is a special relationship. Okay, so I said we have synonyms, there is antonyms, and I said synonyms and determining whether something is an exact synonym is pretty hard. So we were going to make that, checking what is similar a little bit more relaxed. In a sense, we are not going to check whether things are exact synonyms, but we are going to measure the similarity of the words. So similar words are those that are not necessarily synonyms, but they do share some aspect of meaning. Now, for example, skiing and snowboarding, although they are different activities, they are referring to sports that we generally do on snow, and there are some similarity between these words. Like their function might be similar and they might appear in similar contexts. I know we are in Utah, so this might be controversial to put these two words together. So don't be upset with me. Another example is belief and impression, which are not exact synonyms, but they are quite similar. So we are going to be checking how similar two words are, and by that we basically mean how similar the meaning, and that will enable us to study how similar the meaning of two sentences are. Even more kind of, I would say, relaxed version of checking whether something is similar is to check is something related. So this kind of connects to word association in psychology. If I say coffee, you might think about a cup. If I say scalpel, you might think about surgeon, yeah. Okay, these words are totally random. So yeah, you have some associations between words, and they are not necessarily synonyms. They are not necessarily super similar in meaning, but there is some association between them. And basically, if we want to be super precise, we would say that related words are words that are belonging to the same semantic field. So that means they cover a particular semantic domain and bear structural relationship with each other. So, for example, hospital can be one semantic field where we have words such as surgeon, scalpel, nurse, anesthetic, hospital, and so on. So it's all in the realm of like words that are related to hospital, and there are some semantic relationship between them. So surgeon might hold a scalpel, they might talk to a nurse and request an anesthetic, and they all are working at the hospital, right? And similar with restaurant, waiter, menu, plate, food, not similar words, not synonyms, but they are related to each other. So we do want this concept of relatedness because it again is helpful for all of these applications that I have mentioned previously. Okay, so now we want our word vectors to be able to assist us with understanding when words are synonyms, when they are antonyms, when they are similar, when they are related. We want to capture all of that. And to kind of realize such word vectors, we are going to embrace something called distributional hypothesis. Okay, now, do you know what a word artemia is? And if you know, can you raise your hand and not say an answer? Okay, perfect. If no one knows, that's exactly what I wanted, so this is great. So we don't know what this word means, right? We collectively don't know. But let's read these sentences and let's think about which other words could appear in this context. So we have a cluster of is floating within the lake. Biologists study the adaptation of in saline environments. The population of fluctuates with the salinity of the water. And you can observe in the shallows of the Great Salt Lake. So any ideas, like what else, you don't need to know what Artemia is, like, but what else can you fit into these lakes?
Brine shrimp.
Brine shrimp, okay. Any other ideas?
Algae.
Algae, anything else? Yeah.
Lily pads.
Lily pads, I don't know what's that, but very good. I'll actually repeat it as you said. Okay, so we have some ideas, and actually the first answer is what Artemia is. It's a fancy Latin name, I guess. But you all kind of are hinting at something that could fit in the context, like algae, brine shrimp. I'm sorry, I can't repeat yours. So these are all words that can fit into this context, and knowing that, you can then maybe conclude where that, all right, so Artemia is something like algae or brine shrimp, exactly like brine shrimp, and knowing what you know about algae and shrimp, you can kind of infer what Artemia could be. So this is exactly the kind of stuff we are going to embrace with distributional hypothesis. It's super important that you do remember this term, distributional hypothesis. That's something that we mention in the field, and it's expect that you know what it is, which says that words that occur in similar contexts tend to have similar meanings, right? So we didn't know what exactly Artemia is, but we had ideas which other words could appear in those contexts, and then we had hypothesized that likely then Artemia is something alike those other creatures. Okay, so very simple hypothesis, and very effective when we use it and realize it to produce these word embeddings. Before we go into the exact algorithm, I want to cover a few terms that are important. So first of all is vector semantics, which instantiates distributional hypothesis by learning vector representations of the meaning of words directly from their distributions in text. So we have vector semantics, right, as one term, and here we are using this vector representations. So previously I said feature vectors, now we have representations, I keep using embeddings. You can now start to use them as synonyms, okay? What are words distributions in text? Basically, these are statistical patterns of how words appear in a large corpus. So it basically, pragmatics of the first sentence says is you take a large corpus, meaning a large collection of written text, you check how words appear together, and from that statistics, you are going to build these vector representations. So I say here that we are going to use embeddings and representations interchangeably. Basically, now we are working with these vector spaces, and this is where the word embeddings stems for in mathematics. Okay, so these are just some terms we should know about. Why representations? I took this screenshot from my first ever paper in 2016, where this is the first and the last paper where I had to design features for a classifier main, which was what we were doing before we had these word embeddings. And you were yourself also designing features manually by deciding you are going to use bag of words and you're going to record counts or presents or TF-IDF. This is all manual decision. You have decided what's going to appear in your word vectors. Now, with word embeddings, we are no longer doing that manually. Rather, these features, dimensions, the values each dimension in your embedding is going to be learned through the data. And you won't know exactly what each dimension is. So now these representations are going to become what we say black box. We lose some interpretability. Okay. Now we are going to talk about how exactly we are going to realize distributional hypothesis with word embeddings. So here I can also slow down a little bit. So I started to rush after I realized I lost 10 minutes. Are there any questions before we go into how we create these embeddings following distributional hypothesis, which tells us that words that appear in similar contexts that have similar meaning? Oh, yeah.
Are there any readings on this topic that you'd recommend? Or
I will put after the lecture in the website, there is one column with readings. Yeah, I usually just point to Jarofsky and Martin's textbook. Yeah, that's what I usually link there.
Okay.
Okay. All right. So first, let's clarify this term. So we are going to cover how we can produce these vectors, focusing on one software package called word2vec, and this package includes two algorithms. One is called skipgram with negative sampling, the one we are going to talk about today, and the one is continuous bag of words, which we won't cover. And these two algorithms are often loosely referred to as word2vec. So basically, when someone tells you word2vec, they mean, oh, they have produced word embeddings with one of these algorithms, or they use already produced word2vec embeddings, but they can be produced with either of these, and basically the software package is what matters. It has been hugely important for the field. So you might know about NeurIPS, which is the flagship machine learning conference, the top tier conference in machine learning. And in 2023, or 10 years after word2vec was published, it has received the Test of Time award, which is a very prestigious award, meaning, you know, after 10 years, your work is still very relevant. And the committee that awarded this award to word2vec said, published at NeurIPS 2013 and cited over 40,000 times, the work introduced the seminal word embedding technique, word2vec, demonstrating the power of learning from large amounts of unstructured text. The work catalyzed progress that marked the beginning of a new era in natural language processing. So super important work. Okay, and I'm going to give you a kind of high-level overview of how word2vec specifically skip around, like what are we going to do with it? And then we're going to go into bits and pieces in more detail. Okay, so previously, for a given word, which I mark here as W, we have been counting how often each that word occurs in text. Or how often with TF-IDF, maybe we could also check, not TF-IDF, but when we produce the document term matrix, we can also see how often they co-occur with each other. But instead, with skipgram, we are going to train a model that's going to predict how often a word appears next to another word based on their current embeddings. So I have an embedding of the word W, and I have an embedding of word parrot, and I want to predict based off of these two embeddings whether they appear very often together in some small context. And I want to do that just from their embeddings, meaning these embeddings have to be very informative. And basically, I'm going to train my network such that I make those vectors better for this task of predicting whether two words likely appear next to each other. So we are going to use some target word and its neighboring context word, some word that maybe appears two or position before or two position after. And these are going to be our positive examples. These are examples that the classifier needs to label with like, yes, these do likely show up together in a corpus. But I also need some negative examples because you can't train a classifier that needs to predict appear or do not appear with positive appear examples alone, right? So you do need some negative examples. So basically, we are going to sample some random words as being those that appear, that do not appear together with our target word. We are going to train a classifier with randomly initialized word embeddings to distinguish these cases. And through training of this classifier, we are going to change those word embeddings. And then once we are done with that, we are going to use only the produce learn embeddings and throw the rest of the model in trash. We don't care about it. The only reason we have ever used this model is to produce these embeddings that we want to be our embedding layer for various classifiers we have defined before, okay? So again, don't forget that ultimately, what I want to produce is an embedding layer for my feed-forward neural network that's going to do classification for some downstream task like sentiment classification. And I'm going to produce those embeddings by training another model. But once I have trained that model, I don't care about that model. Those models just needed to produce embeddings for me. Okay. So here we have some portion of a sentence, lemon, comma, a tablespoon of apricot jam, a pinch, and so on. My target word here is apricot. And my neighborhood, my window, is 2 words before and 2 words after, including the target word. So I have these 5 words as the neighborhood, a window I consider. I'm going to write the probability of plus means that these 2 words, W and C, appear together in this window. That means that's a probability of being plus means that these 2 words appear together. And if I observe these 2 words together, I want the probability to be as high as possible. Again, I'm going to be a little bit repetitive, but my goal is to learn embeddings of W and C such that some function of these 2 embeddings has a high value when they appear in the same context and low value when they rarely appear in the same context. This might be too much to ask, but now given this goal and given some functions you have learned in this class, do you have idea of what we could use? Sometime previously, we had also a problem where we wanted to have high value, high probability when something. Yes, please.
Use like vector.
Okay, I use vector embeddings and then what?
Then cosines vary.
Okay, yeah, so if I have a embedding of W, I have an embedding of C, I think their cosine similarity is going to be high when they are similar and low when they're not. That's a great step. What if I want to also probabilistic function? What else have you used previously to get the probability for high value being what?
So my function that's pushes.
Does any function comes to mind? Sigma, exactly, right. So previously, we had the problem where we wanted the dot product between weights and feature vectors to be high, to be associated with high probability. And we kind of have a similar issue here. We have 2 vectors, and when they are similar, we want the some function value to be high, and then we want this to be associated with high probability. So this just goes to show that sigmoid isn't just part of logistic regression. It's a mathematical function that you can use for various states, right? So previously we used it for logistic regression binary classifier. Now we are going to use it for learning embeddings. Yeah.
Are we using sigmoid because when we get that sort of probability distribution, all these are gonna be independent probabilities as opposed to, say, using something like softmax, where all the probabilities are dependent on one another?
The difference between sigmoid and softmax is only that sigmoid takes one real number and softmax takes one more of them. But they are trying to achieve the same purpose. So with sigmoid, you have one real number and you're just going to squash it between 0 and 1, right? With softmax, you have, let's say, 5 real numbers, and you want to squash each one of them between 0 and 1, and you want their sum to be 1.
So we're only dealing with one value
Yes.
right now?
Yeah.
Okay.
Yeah, that's right. And to make all of this a little bit more concrete, so here, again, this equation is just the definition of sigmoid function. We have the plot of sigmoid function, and I have set as a goal to learn the embeddings of W and C such that if they appear together in the same context, we get the probability of 1. And basically, the way I go about this is to increase the similarity, the vector similarity of these two vectors, and then apply sigmoid function to them. So let me put it here. So maybe it's going to be helpful that I actually write this down. So I have my W, I use to denote my target word. So that's the word that's in the middle of the context. And C is some other word. It's maybe part of the target's word context, maybe it isn't. We are trying to predict. And our goal, and I should have written that a little bit more nicely here, I'm basically overloading C and W to mean the similarity of the embeddings of the word W and word C. So here on the whiteboard, I'm going to be slightly more precise and use this notation to denote the embedding of W. So this is some high dimensional vector, right? It's going to be element of RD. And similarly, embedding of C. So I take their similarity to be here. Dot product, you said cosine similarity, that's both fine. So similarity between the embedding of W and embedding of C is going to be their dot product. So remember, that's just the sum of the product, element-wise product. Okay, I want, when this similarity is high, I want the probability of them to be positive. I want, not positive, I want it to be close to 1. So let me do this. So like when similarity goes to infinity, plus infinity, I want the probability of W and C appearing together in the same context to be close to 1. Or I should say, instead of just exactly 1, I should say it should go to 1, right? And when similarity, and here I'm using dot product, so when it's very low, I want the probability of them to be appearing together to go to 0. And this is exactly what I can achieve by applying sigmoid to similarity. So sigmoid of similarity will then give me this behavior. So sigmoid behaves as a basically probability function here if I give it as input the product between the embeddings of the target word and the context word. Okay, so that's our intuition. And then as you know, with logistic classifier, the problem here is that I didn't tell you what these embeddings are, right? And basically they are randomly initialized like the weights were, and we need to iteratively change them by predicting whether these words appear together. And we do have a label of whether they appear together, which we have just taken from this large corpus. If they appear together, they appear. If not, they don't, right? Okay, is that intuition clear? We are going to go now into details. So some details certainly aren't clear now, but is it overall intuition clear? Yeah, please.
This similarity function is literally just a comma, right?
Yeah. Okay. So this brings us to skip drum. Actually, what is it? Okay. So I'm just going to write these equations. I feel like might be helpful to. I think we actually have seen this plenty of times, so maybe I want to write it all down. So we are looking at the probability that a given word and given context appear together, and context is composed of more than just a single word. And we assume that this is independently and identically distributed, so we can write this probability as a product of individual probabilities. And now I have just told you that we are going to use the sigmoid of the dot product of each one of these as the probability of appearing together. Okay, so maybe actually I'll write it here. So we have C. Okay. It's going to be C1, 2, imagine 3, 4, 5. All right. Okay, maybe just 3, 4. I don't know how exactly. Okay, so this is our window. Remember previously we have apricot something something, right? That's one of the windows that we have extracted from a corpus. We downloaded some written text. We said we are going to use a window of length 5. And from this window, we now have actual words appearing in that window. That's our data. So this is C from 1 to, I guess, 5 or I don't know. Okay, and we are looking at the probability that our word here appears in this context. And we assume that the probability of the word appearing with the first word in the context is independent of whether it appears together with the second. So this is again just IID assumption we always make most of the time making machine learning because it makes things easier. So we can write this as a product of probabilities. Okay. And now here is where I introduce sigmoid. So this probability I say is the sigmoid of a dot product between the embedding of W with the embedding of this context word. And this dot product is basically measuring similarity between these two embeddings. Okay, so this is how we measure the probability. Of course, we are going to use negative log likelihood. So I'm going to apply the logarithm to this, which will make this product into a sum of log probabilities. Okay. Now, what are we trying to learn here? These are our weights. These embeddings are the things we are trying to learn, trying to change iteratively with our gradient descent algorithm. So here in this visualization, we see that theta or weights are embeddings of all the words in the vocab. And we are going to use different embeddings for the target, like when that word is a target word and when it becomes as the context word. So for example, if here we have apricot, we are going to use this embedding coming from the top. You see the top part of the weights there. If we had used apricot as a context word, we would use this different embedding. So our weights, or here denoted as theta, is going to be a matrix of the size of vocabulary times 2, because for every word we have 2 embeddings. So this is of the size of the vocab, and this is of the size of the vocab. And here each row is d-dimensional because that's an embedding of the corresponding word in the vocab. So we are going to basically pick these vectors when we need them here. And then we are going to get this probability that this word appears in this context. And we do know whether it appears or not. Then based on that information, we can measure the loss and back propagate and change these numbers such that next time we make this prediction of whether they appear in this context, we can make the better prediction. So standard negative log likelihood training is just important, and it's a bit maybe confusing now that these embeddings are our weights. That's what we are trying to learn. Once we are done with training, we are going to keep, I believe, only these embeddings, which we kept for target words. So these embeddings are in the end what becomes our embedding matrix or embedding layer. Or I will say this differently. You will have here one embedding for word, like let's say zebra, and you will have it again, another embedding for zebra. But in the end, we need just a single embedding for zebra. So we are going to take only those that we have trained for when we needed embedding of that word for it being a target word. Is that clear? It's just a little detail that can be quite confusing, I think. Like, why do we see 2 sets of embeddings, and like, why do we remove one of them after? I hope that's clear now. Okay. So let me see whether I want to go through this. Okay. Okay, so we have defined what the probability is, and I keep saying now we are going to change these embeddings, which behave as the weights of our models, such that we get the best probability given what we know is true. Like for a given word, we do know whether it appears in a given context because we have extracted that context from existing written text, right? So we are going to define a loss function, but for our loss, we are going to need this notion of what the positive example is. So positive examples are going to, first of all, we are going to take some corpus, large collection of written text, such as original work had used internal Google dataset consisting of various news articles with 1 billion words, and resulted with a vocab of the size 692, which also tells you how large a vocabulary can be. So now imagine that for every vector, every word, we actually produce 692,000 dimensional vector. Not nice, right? Given that most of its dimensions would be 0. So now when we have this collection of texts, basically you can decide on a sliding window size, which is a hyperparameter. I believe they use the size 5, and you just slide it over that text. And in this way, you get a bunch of windows, right, from a piece of text. And this is your data, where you know that the word in the middle, that's the target word. The words next to it are its positive examples. So you can produce a positive pair from a word and the words that appear before and after it in your window. These are going to be your positive examples. So here I have an example: pour the milk into the, pour milk, the milk, and into milk. They are all positive examples. Okay. Now with negative examples, it's a bit trickier because you have many more words that are outside of the context. So basically what you do here is add some noise word as your negative to produce a negative pair. So basically you sample from the vocabulary to have to produce a fake negative pair. And here the probability distribution with which we are sampling from the vocabulary, its exact form, it doesn't matter. I will tell you what it means. It just means that we are going to sample words from the vocab which have low frequency in this corpus more. We will sample them more to produce this fake negative example. And the idea behind that is, well, if they are appearing rarely in the corpus, then it's very likely that they won't be a positive pair anyway. So that's the idea behind that. And then, of course, sometimes you can hit something which is actually a positive example, and this is where this is slightly noisy, but that's okay. Negative examples can be noisy, and they can, if you're doing this sampling from the vocab, you're actually introducing the diversity of things that don't appear together. So now you have your positive and negative examples. Don't forget, did I write them here? No. No, I did write somewhere what's a positive example on the slide. Yeah, so just remember positive. When I say positive example, I mean a pair of two words are a positive example when they appear together in the context. Okay, so now when we know the notion of positive and negative example, we are going to write the loss down. Yes, please.
So you said that the negative examples could potentially show up. A positive example could show up as negative. Why don't we just do a double check? Like we draw from that distribution, say we get the pair, to say if it's in the set positive, so.
Yeah, I think honestly, I don't know this detail, and maybe the authors did something smarter, and I didn't cover every single thing that they have done to produce negative examples. I would just, my first gut reaction to that is that we are working with scale now, right? So just to produce all the positive pairs, you have a lot of pairs. And now if you want to check for every word, or you are creating this negative example, is it or it's not. Most likely, yes, you will have some cases, but this is really important. It's not because the solver is going to learn from a little bit of cases.
Essentially low enough probability that the computational process is not worth it.
That's my, like intuition about this, whether this is true or not in their own realization and validation of word2vec, I'm not sure. Yeah. Okay, so let's see. Use this one. So I'm going to derive what the loss here is going to be for a single window. Then you can average the loss for more than one. And in the next slide, there will be gradient equations, but we won't derive them. Okay, so what is our loss here? Is going to be, as always, negative log probability. That's what we are trying to minimize. So we are trying to minimize negative log probability. And here I will repeat that we start with some positive, some word is going to be positive. In a sense, oh, this word appears together with our target word. And we will have a few negative examples. And how many is a hyperparameter k? I remember k being important, how many negative examples, but I don't remember how many there are. So, but it is important hyperparameter, like how much of negative data you will see for a given pair. So given this for our target word, I want to maximize the probability or minimize the negative log probability that this word, that the probability of this word being with this word is high. And I want to also maximize probability that this word does not appear with these words. So this is what I'm writing down. So I'm maximizing the probability that the target word W is appearing with my positive context word C positive. I'm immediately using the assumption, IID assumption, of writing the product here from I equals 1 to K for the probability that the word, target word W, does not appear with the word C negative I. Okay, product, because I'm assuming these probabilities are independent of each other. Okay, so now we have that. We are going to use, as always, the property that log of A times B is a sum of logarithms, right? So this becomes negative log probability of a positive of seeing W with C plus, C positive. Sorry, guys, I'm just making this up at this point. And this also becomes a sum. So minus sum of I to K of these log probabilities of not seeing the word W with C negative I. Okay, this one here, probability, sorry, just a moment. So this one here is the same as 1 minus probability that I will see this word together with these other words, C negative I. And then if you remember way back when I told you that sigmoid is had that property, sigmoid of minus x is sigmoid of something x. So basically that's what we are kind of going to use here. So here I said previously the probability is the sigmoid between the dot product of the embedding of W and the embedding of C positive. So this is something we have just agreed we are going to use as probability. And here I'm just using the sigmoid property to write this down as logarithm of sigmoid of embedding of W times embedding of C negative, but everything is set to minus here too. So this is where I use that property of the sigmoid. And here is going to be plus. Okay, so no, it's not going to be plus. Sorry. Okay, so basically with this loss function, what I'm minimizing is the log probability that log probabilities. And for the positive pair, that means that we are going to maximize the embedding similarity of these target words embeddings with the embedding of the context word that actually appeared with this word. So we are trying to maximize their similarity through this probability. And on the other hand, for these negative pairs, we are trying to maximize the distance or dissimilarity of the target words embeddings with the embeddings of these negative context words. So this is what we are trying to achieve with minimizing this log probability. Okay. Now, I don't want to derive this, but of course, the next step is to then do derivatives with respect to our weights, which are the embeddings for context words and embeddings for target words. And once you have those gradients, then you can start to use gradient descent. So basically, your weights are these embeddings, and you are changing them by doing this gradient mapping. So remember, these are your weights. Now I have calculated these gradients, and I can change each one of these rows just slightly such that predicting the probability of what appears together is higher and what doesn't appear together from the embedding similarity alone becomes more and more correct. Okay, so before we move forward, is there anything unclear in these derivations? For me, it is crucial that you understand that we are learning embedding matrix such that we can plug it into another model. And so this is the embedding matrix we are learning and we care about in the end. And here we do, we have implemented this model, these gradients and everything. Once we're done with training, we can, if we are sure our embeddings are right and we will never use this code ever in our life, we could throw it away. We don't need it anymore. And we use these embeddings to become the embedding layer of our deep averaging network later. And basically what you're going to do in the assignment. Yeah.
Just trying to understand the last step when we are doing the sigmoid for the negative examples. I saw that dot product of the embeddings is going to be a negative of the is going to be the negative dot product of those. Is that because we have that 1 minus the probability, and when you have like log of 1 minus something, you can do the negative of the operation?
It's not about log, it's about so logarithm is still here, staying here. It's about the property of the sigmoid that I forget now, but let me show it. The one I'm thinking of that we are using here. I hopefully can find it. Maybe I know I had it in one of the slides, but now, oh, here it is. So you have 1 minus. So it basically comes from this property of the sigmoid function. So it comes from there. I don't know like now how to put it all together, but that's what we have used in this step. So just changing the yeah.
Okay, yeah, I can see it.
Yeah. So if this is this dot product is z, I guess. Then we had, if you put 1 on the other side, you will get sigmoid of z minus 1 equals minus sigmoid of minus z. If I multiply everything by minus 1, I will get what I need. I will get the sigmoid of minus z, and then it's going to be minus sigmoid of z plus 1, which is this.
And if I'm understanding this correctly, when we then go about minimizing this log loss, we're maximizing the positive embedding, but then because we have that negative term in there, it's going to be maximizing the embedding distance. Okay.
So yeah, here this similarity to minimize to minimize this log probability, this similarity needs to be as high as possible. To minimize this negative log probability, the distance needs to be as high as possible.
Okay.
Yeah.
Or also like the similarity
Similarity,
is small as possible.
Everything is symmetric.
Right.
Yeah. Oh my God, let me go. Okay, so you will find about 1 million resources about embeddings on the internet, and there is really some fun ones. So here I have shared this one on Programming Historian that had, I think, checked how to go about very old recipes using word embeddings. So definitely you can find a lot of interesting use cases out there. So, you know, I suggest exploration for sure. Okay, there is also word2vec is just one type of word embeddings. In 2014, it was all the rage to try to produce as best word embeddings, and we will talk about how you can, analyze and compare word embeddings next time. So you will see other kinds, and I think in the assignment we also give you glove embeddings. This is not so important anymore. There might be some other embeddings that are slightly better, but if you end up using these word embeddings with a small fast-forward neural network, it means that your problem isn't super complicated anyway. So most likely, slightly better embeddings won't help you anyway. I do also want to draw attention to this library, fast text, which is the library for learning word embeddings. So if you have a new specialized domain and have a large collection of written text there, and you feel like, oh, if I just had good word embeddings for this domain, I can actually, with a feed-forward neural network, I can do it really well. And then it's really worth to just train your word embeddings on this large collection of your own text. Keep in mind that I told you that word2vec has been trained on this Google basically news article corpus. Is going to be good for like general topics, but if you are interested in developing NLP method for medical or legal domain, they might not be sufficient for your purposes. So that vocabulary has a lot of words, but then a lot of medical words don't just appear randomly in news articles. So sometimes you would need to retrain these word embeddings. 10 years ago, this was like, we would never do that ourselves. And now your compute, like if you use CHPC, I believe you can do that easily. Okay, so let's stop here. Next time, we are going to just do this exercise to see whether we understand the differences between sparse bag of words representations and embeddings, talk a little bit more about embeddings, and then move forward. Okay, thank you.